My guest today is Joachim Dengler.
Today I have a theme called Is Nature's Carbon Sink Failing? And before I start with the talk, let me give you a few remarks on my background. I'm a PhD in physics from the University of Heidelberg. I did a postdoc in lot with image analysis, partly at the MIT AI lab. And there I wrote what in Germany they call the Habilitation thesis, which is a precondition for becoming a professor. And that is foundations of optimal model building. And now what I learned at that time turns out to be quite useful nowadays for modeling climate effects. And there I also had a cooperation with the Harvard Medical School. At that time I did brain models and matching intraoperative with preoperative brains. Was quite an interesting time. And then I had a company of my own where I had 2 patents in fingerprint analysis. Then I did IT consulting for about 25 years. And during the last 5 years, I am now in climate research. I had, meanwhile, 2 peer-reviewed papers, mainly on the relations between emissions and concentrations. And you will see today's talk that will also play a certain role. Beside that, I have a blog. It is essentially partly in German, partly in English. And the English part you can reach with this link. It is Klima with K minus Fakten with also K and .net. And if you don't use the extension, you first land in the German version, but you can then easily switch to English. Okay, let's dive into it. Now I was kind of a bit surprised over the last 6-8 weeks in a lot of German and also English newspapers. We got the latest climate alarm with failing carbon sinks, and it was surprising because over the last 20 years I never heard from the mainstream that there were carbon sinks. We only had lots of anthropogenic emissions and rising carbon concentration, and nobody was talking about sinks, and suddenly they talk about sinks, and in particular about failing sinks. So not only do we have rising carbon concentration, but failing carbon sinks now even make it worse. And the timing was perfect. It was just before the great climate conference, COP29. And for example, in The Guardian, the title was Trees and Land Absorbed Almost No CO2 Last Year. Is nature's carbon sink failing? The sudden collapse of carbon sinks was not factored into climate models and could rapidly accelerate global heating. And also a hint to another article. If what happens to the world if forests stop absorbing carbon? Ask Finland, and so on. And you read similar things in very different papers. And here one more sentence from The Guardian in 2023, the hottest year ever recorded. Preliminary findings by an international team of researchers show the amount of carbon absorbed by land has temporarily collapsed. Okay, already now it's a bit relativized. They talk of preliminary findings and of temporary collapse. So there may be some hope. The final result was that forest, plants and soil as a net category absorbed almost no carbon. Now, what do we make of that? How do they come to such conclusions? Because let's first think about it in a naive way. when we talk about land sinks are essentially photosynthesis. Yeah? So the conclusion would imply a significant reduction in photosynthesis, which is the primary land sink factor. But such a reduction could not be found. I suppose if we had a reduction in photosynthesis, we would have had lots of headlines. It would mean that food production would fall. It would mean that timber production would decrease, yeah, because if there are no wood growing, then you cannot make any wooden products, yeah, and also the greening of the world would stop, yeah, so or would decrease at least. But nothing of this can be actually observed, yeah. Looking at the kind of, even if we have global warming and CO2 increase, photosynthesis is supposed to increase due to increased carbon concentration in the atmosphere, which is CO2 fertilization. Yeah, we have definite proof also in a paper in Nature that 50% of the greening of the earth, which has been there over the last 30 years, is essentially due to CO2 fertilization, due to the increased CO2 in the atmosphere. Also, photosynthesis is optimal at 30 degrees centigrade. So if the average world temperature increases, we would also expect more photosynthesis, yeah, rather than less. Yeah, so by means of naive thinking, we kind of have doubts about such conclusions. Now they refer to a scientific article. What does it say? The title of the article is Low Latency Carbon Budget Analysis Reveals a Large Decline of the Land Carbon Sink in 2023. Now, that's interesting. The paper is not primarily looking at individual phenomena such as the reduction of photosynthesis or the end of ocean absorption, but it's looking at the global carbon budget. And this is something quite familiar to me. And from there, they start making they postulate changes of the land and the ocean sinks, yeah. And then they also elaborate of some example there, but the primary reason why they write the paper at all is because of the global carbon budget. Now the question is this conclusion justified? Now let's look at the authors. They're a mixed team from China, England, France, Germany universities, and Microsoft Research. Well, I don't want to claim anything, but I'm asking myself, why is Microsoft Research involved? Could there be a conflict of interest? I don't know. I'm just asking. And also, I saw the paper is not peer-reviewed. It's just a preprint. Nevertheless, the media in many countries claim it to be scientifically reliable. Yeah, normally they are insisting very much on the peer review. Yeah, when we have discussions with people. Okay, now let's look at the details of the study. Yeah, and trying to understand the reasoning for the claims of reduced sinks. The key point is that CO2 concentration has grown significantly in 2023. Yeah, we look at this bar, which is much larger than the 2022 bar. Oh, sorry. And this happens after there has been a downward trend since 2016. Yeah, since 2016 we have a downward trend of CO2 concentration growth. Yeah, this diagram doesn't show concentration, but concentration growth. Yeah, and measured by two different methods. Yeah, MLO is Mauna Loa, and the other one is measuring on the sea surface, worldwide sea surface. Yeah, but the measurement data are rather similar, so we don't worry. We can from the diagram at least we can see we can trust the Mauna Loa data because they coincide pretty well with the other ones. On the other hand, anthropogenic emissions have been rather constant from 2022 to 2023. There is a very, very small increase in 2023, but it is, if the gray bars are anthropogenic emissions, if we added error bars here, yeah, the error bars are at least 10 times larger than this very small increase. So we could justify saying even over the last 10 years, emissions have been constant. Yeah, this I think I said that in my last talk. But interestingly, now we hear it from the other side. Yeah, they say, and you see, in the argument is, fact is, anthropogenic emissions didn't increase, but CO2 concentration increased. Therefore, the sink effect must have decreased. Yeah, because the sink effect is the difference between emissions and concentration growth. Yeah. So, and the claim is that must be due to something what happened in the land and ocean sinks. Yeah. So, and superficially, this looks quite compelling. Yeah. And now let's see what's happening with the data. Now we look at the data, and to understand this phenomenon for the first time, I had to look at monthly CO2 concentration and concentration growth data, because with the yearly data, it's not sufficient, because you see 2023 is the last year which in the time series, and it's difficult to make conclusions if you take the whole average of 2023. Yeah. And so first of all, we look at the CO2 concentration. Yeah, and here I can also start showing what I did with the data. The original Mauna Loa concentration data have seasonal wiggles. Yeah, you see a steep increase of concentration and then a decrease, or the other way around. Yeah, and it so happens that the decrease of CO2 concentration happens during the spring and summer of the northern hemisphere. Yeah, and so that's the time when we have maximum photosynthesis. Yeah, and we can ask why doesn't this average out with the southern hemisphere? The simple fact is the northern hemisphere has twice the land mass as the southern hemisphere. Yeah, so any effect which is land dependent is stronger on the northern hemisphere, and therefore we see these deviations. Yeah, so we can clearly say these wiggles are due to photosynthesis. And we look if we look at the raw concentration data, we don't see anything really alarming in these data. Yeah, we can hardly see any difference. We have a certain trend in the data. Yes, they are growing. Concentration is growing. Then we have the seasonal deviation, but they look all very similar. Yeah, so we in order to get a better understanding, we must look at the monthly changes. Yeah, and now here it really becomes interesting. When here we, but if we take the raw data, monthly changes of the raw data, then the seasonal effects would absolutely dominate the diagram, and it would be distorted. So we have to do something what they call to deseasonalize. Yeah, and so I did this by calculating the average of the cyclic changes over the whole period from 1960 to 1923. Yeah. So I looked what is the common cyclic changes over all those years, and I subtracted that. Yeah, and from this I got the orange curve, which is hardly to be seen. And to be on the safe side of life, I also displayed the yearly Mauna Loa concentration data, which we also have. Yeah, and so you see the deseasonalized monthly data perfectly fit the yearly data also. Yeah, and the yearly data are interpolated by a cubical spline, yeah, which makes it a bit smooth. So smoothed yearly data is essentially the same as deseasonalized monthly data. Yeah. Okay. Now we look at the CO2 concentration growth of these deseasonalized data. And now the first thing we see, yeah. First of all, yes, there is a sharp increase in 2023. Yeah, we can agree with that. Yeah, but obviously, being a heretic, I'm asking myself, why was nobody alarmed when in 2021 there was such a incredibly strong negative spike here, yeah, which is the so we had whereas here on average we have also monthly concentration growth bigger than zero, but here, for example, we had a large spike smaller than zero, which is much larger than the peak here in 2023. Also, positive peaks are not so unusual. We had them in, I think 2018 was this, and here it was 2016. Or between 2015 2016, there was an even larger spike. nobody seemed to care at that time. That was the time when the Paris Climate Accord was finalized, yeah, and so again with a bit of naive argumentation, we could say, well, these spikes are actually nothing special. Yeah, we've always had them. Yeah, even in 1985 we had a spike which was not quite but nearly as large as the one which we have in 2023. Yeah? And obviously we have also lots of negative spikes. Yeah, that's so no wonder. Yeah, and to get a bit more understanding, we can smooth that curve, and it's quite wiggly. And but here we, in fact, when in the smooth data, we can see a little bit of a trend since 2020. Yeah, it's kind of goes up, yeah, slightly, but not alarmingly. Yeah. Now let's start to get a bit more analytic understanding, starting with the published emission and sink data from the Global Carbon Project, or Global Carbon Budget, they call it. And this implies that more than half of the anthropogenic emissions, which is the gray part, plus the land use change also, approximately half of that are removed from the atmosphere by land plants, the light green, and ocean absorptions. It's the dark green part. And the blue is the rest of carbon which is added to the atmosphere. But you can see that the trend of the sinks is increasing. Yeah, it's not decreasing as the long-term trend. Yeah, and so we are a bit surprised that it should suddenly collapse in 2023. Yeah. But also in this diagram, which displays the past, there has always been very large short-term variation, especially in the land sink. Yeah, you see there are big maxima and minima. So we have had that. If it happens, we can say we have had it before. Yeah, it's again, it's nothing new. Now let's start really doing analytic work. Yeah, and now the diagram from the previous page is now condensed in the. Here we have the anthropogenic emissions. Here we have the concentration growth, and here we have, with a negative sign, the green. That's the sum of the land sinks and the ocean sinks, both together. Yeah, we just mix them together. And now what we need to know, that we can make use of a bit of physics. We can make use of mass conservation, or you could also say the continuity equation. Concentration growth must necessarily be the difference between the total emissions and the total absorptions. Just compare it with a bank account. Yeah, your balance, your capital growth at the end of the year is the sum, or the difference between all your income, total income, minus all total costs. Yeah. So, and this must be true with all time scales. Yeah. And now, but we are not talking only of anthropogenic emissions, but we're talking about total emissions. Yeah? So we can split the total emissions into anthropogenic plus natural emissions. And the key point of my argument is we must not discard natural emissions. Yeah, and you know that, Tom, that mainstream people do not like to talk about natural emissions. Yeah. So, but it is necessary to talk about it. Therefore, what we call the effective sink, which we saw in that previous diagram, this is what I call effective sinks, are not only actual absorptions, but they're the difference between absorptions and natural emissions. Yeah, if we have this equation, concentration growth is anthropogenic plus natural emissions minus absorptions, we twist it around. The difference between emissions minus concentration growth, which we call the effective sink S, is the difference between absorptions and natural emissions. You know, this is up to now. This is not yet a model. Yeah, this is scientific necessity. That's mass conservation. But now we start modeling. We model these effective sinks. We say, okay, we assume that absorptions are proportional to concentration. And because we don't know any better, we do the same as the mainstream. We assume natural emissions to be constant. Yeah. That's our simple model. And in the paper, in the first paper I wrote, I made very successful predictions with this very, very simple model, yeah, of future concentration. Yeah, for example, I predicted the up to now known 21st century concentration data by 20th century concentration data, and it was a very, very precise, perfect fit. Okay, so we tried to explain the concentration growth with the linear sink model from this model equations, which we just derived. We can reconstruct what we could call a noise-free concentration growth. Yeah, we just switch the equations around. Concentration growth is the sum of anthropogenic emission plus natural emissions. That's our basic primary definition, but we model natural emissions by a constant and model absorptions with proportionality to concentration. Yeah. So total emissions are modeled by anthropogenic emissions and natural emissions, which are assumed constants, whereas absorptions are modeled being proportional to CO2 concentration. We see that there has always been significant variability of concentration growth, but the model is nicely in the center, so we get nevertheless very precise predictions of future concentration. Yeah, that because it's really symmetrical, and so these wiggles, they average out in the long run. Yeah, but now it seems here that in 2023 it doesn't quite average out. Yeah, that's we have to admit. Yeah, as a small side remark, I'd like to mention, You remember during the 2020 when we had COVID, people were debating and arguing, why don't we see a reduction of concentration growth because of the strongly reduced emissions in 2020. We had a strong reduction. And when we use the model data with the sink model, we do in fact see a reduction of concentration growth, a really significant one. But unfortunately, we had a positive wiggle in the same year. We had a spike in at this point I say an accidental spike in the other direction. So the hoped for reduction of concentration growth was overcompensated by some natural effect here, which we yet have to define what it is. So, but now we have two things. We see that in general we can model very nicely the concentration growth, but something strange happened in 2023. But again, what happened in 2023 was not so unique because it happened also before. In 2016 it happened also, and nobody was worried. And also something the big negative spike was in just after 1990, that we in one of our last talks we discussed that this was due to Pinatubo, the volcano, but so we have various effects, but fair enough, give the devil its due, we do have a spike in 2023. Now, up to now, we had assumed, together with the mainstream, that natural emissions are constant. Now we ask what happens if natural emissions are not constant. So we relax the model constraint, letting natural emissions be variable. When we assume linear absorptions, we get, and we have the same equations as before, only instead of the small n, we use the capital Ni. So we have varying natural emissions from year to year. And turning the equation around, we can actually compute the natural emissions from our measured data, concentration growth and emissions, and our model absorption constant, which we have calculated before. And now we state variations of natural emissions just do not exist in the paper which claims the failing sinks. When we introduce natural emissions, there is no need to change the sink effect, no need to change the A here, which represents the sinks, A times concentrations. Therefore, in order to understand the recent concentration growth, we should focus on natural emissions rather than sinks. And here we also see the blue line are the computed raw natural emissions. The green line is our original linear model, the constant natural emissions, yeah? And we see that on the average, natural emissions reduce to the green line. If we do something intermediate, if we do some smoothing of these measured emissions, we see that it is going up and down on the green line, but at the end, towards 2023, we see a real upward trend. Yeah. Okay, but again, these trends have been there also before. Yeah. Okay, then we start with the new assumptions. We assume that natural emissions may be temperature dependent. And when we look at the sea surface temperature, and here we have monthly data, and for this talk, I in fact extracted the very latest monthly data, yeah, which go until the end of November 2024. Yeah, so the last data point is November 2024. Yeah, that's which already relativates the fact that there was a peak in 2023, but already now it has gone down a bit. Yeah, not completely, but at least it has not increased further. Yeah, we already see a downward trend. Yeah, and the point is, again, we need to use monthly data, otherwise we don't get the necessary precision. And here again, I also looked whether we need to deseasonalize sea surface anomalies, and there is in fact a small seasonal trend in global sea surface temperature. You see the small blue peaks are a bit smoothed, yeah. But the effect is extremely small, yeah. So sea surface temperature, there is no big asymmetry between northern and southern hemisphere, yeah. And let's compare again. Now we have one problem we do have when you look at the natural emissions. They do not show a trend. Yeah, they over the whole time, over the whole 60 years, there is no trend. But temperature, we do have a trend. Yeah, we have warming from 0.2 degrees anomaly to nearly 1 degree. We have a clear trend. Yeah, and so if we want to relate the two, we must think again. Yeah, and this is let's say a little trick or a mathematical procedure which I described in my latest paper and also in my last talk here. It is a fact that over the last 60 years there is a strong correlation between global temperature and CO2 concentration. And here we can see that CO2 is very closely related with the trend of global temperature. And I need to state, I am not interested and I don't care about whether there is a cause or not. Yeah, I don't know whether there is a cause, whether CO2 causes temperature or temperature causes CO2. Well, I will make a statement about temperature causing CO2, all right, but about the other direction, I don't know. Yeah, I don't deny it, but I also don't claim it. Yeah, so I'm not for this argument. I'm not interested in the discussion. Yeah, I'm only interested in the mathematical relation. Yeah, and that's why if the sink effect is temperature dependent, but also concentration dependent, which it is, we cannot tell whether it comes from the concentration or from that part of the temperature which is linearly dependent on concentration. So we actually can be only sure about the temperature effect when we look at the residual temperature, when we subtract the CO2 relation from the temperature. Then we get also a zero mean signal which has no trend. Yeah. And this is what we found in the natural emissions. Yeah. And then when we have this, we can redo our model by adding a temperature term to our linear model, which the linear model was A times Ci plus, we had a minus n, but now the variables change. Yeah, we have a slash or an a prime times c. This changes when we introduce temperature, plus a temperature effect, plus a constant. And those who are more interested in the temperature-dependent model may have a look into my scientific paper, which is, I have a link on the last page of the slides. Now, when we do this, then the computed concentration growth, emissions minus sink effect, is the orange curve. And you can see this models the different spikes, at least partly, not always perfectly, but it models really perfectly the 2023 spike. Yeah, you see, it says when you include temperature, which you actually have to do, this exhibits extremely well the recent exceptional observations. Yeah. So, what are our conclusions? The authors of the paper, which caused a worldwide stir in the mainstream media, have an incorrect understanding of the worldwide effective sink systems. Besides the absorptions by plant growth and ocean absorptions, there are natural emissions which do not appear on the radar of mainstream climate science. We just have to state that. Natural emissions rise with temperature. You just have to imagine warm beer. Yeah, that says it all. Yeah, the CO2 is gone when you warm your beer. Yeah, it goes out. Yeah, and so and the rising emissions due to temperature trend proportional to CO2 concentrations are compensating by rising absorptions which scale with CO2 concentrations. Therefore, actual long-term trends are hidden as long as temperature correlates to CO2. but short-term heat fluctuations directly translate into emission fluctuations. The heat spike in 2023 is a very instructive visualization of this effect. Okay, that's it. Here I have all the links. First, the link to the Guardian article, then the link to the preprint, which I discussed, then here all the raw data which I used, and here my own publications, which were at the basis of this talk.
And just by the way, I'm going to put the PDF version of your slides up on my Substack, so people can go there and they can click on all of your links and learn more about this.
Yeah.
So overall, in the huge big picture, is it just another case of people trying to scare us about a fluctuation that we've seen fluctuations like this in the past? It's a short-term thing.
Yeah, I think there may be a few a few factors. Yeah, first of all, because the skeptics like me and others, like Roy Spencer and Professor Fahrenhold, they keep insisting on the sink effects. Yeah, and in Germany there is a group called 4-pi solutions. Yeah, and they are some professors and industrialists who are proposing a plan B for the climate. Yeah, they accept the climate, the IPCC climate stuff, but they claim that half of the emissions are compensated by natural sinks. Yeah, and so they say, if we do not reduce our emissions to zero, but just to 50%, then we are done. Yeah, because the sinks are not related to emissions, but to our concentration, to the concentration. Yeah, so the sink effect stays the same, and if we have only half of the emissions, then we stay at 420 ppm forever. Yeah, so that's their concept. Yeah, and my suspicion is they want to. The alarmists want to scare people that they don't follow the plan B also. Yeah, they want to insist on absolute zero. Yeah, that's the idea. And that's one thing. And the other thing is, I think it was you see, always shortly before a climate conference, they need something to write about. Yeah, and this was very nice to write about. Yeah, to another factor, another unknown factor to scare people. Yeah, and so, and you see, for me, my motivation was just the other way around. You may remember in our last recording, I said that up to now there are not many practical applications of the temperature dependence, because for predictions it's actually better to use the simple linear model. Yeah, and so I took the historical data, the ice core data, to explain the temperature effect, but in the really in the current data, the temperature effect didn't play such a big role. Yeah, but now when I saw this, I saw, well, this is an invitation also to motivate the temperature dependence of the natural emissions, yeah, and also to introduce the natural emissions into the discussion, yeah. You see, I am not an either-or guy. You see, there are some people who claim there is no effect of the anthropogenic emissions at all. It's all natural emissions. They are so much bigger than the anthropogenic. So anthropogenic emissions are drowned in the natural emissions. I don't agree with that, but I think it is important to account for the natural emissions, yeah, and to look at them, yeah, and to see what's their role, yeah.
So I am looking at the Keeling curve data here. It looks like it starts in the 50s with the instrumental readings. What do you think it would look like if we had data with instruments back 800,000 years? Do you think it would be pegged at 280 for hundreds of thousands of years, or what would it look like? I would suspect that it fluctuated naturally back then too, but what do you think?
Well, I mean, the last 800,000 years it did fluctuate, but the truth of the matter is it fluctuated around 280. Yeah, it went in the ice core data. It went down to 200, and it rose to 290 or 300, and then it went down again. Yeah, so there, the last, let's say, the last million years, it was pretty much fluctuating around 280, yeah, depending on the temperature. Yeah, when there were ice ages, it went down, and when there were warm periods, it went up again. Yeah, but the time before is interesting, and I had a discussion recently with some interesting people who had an exhibition in Heidelberg. They were also skeptics, I must say. Otherwise, they wouldn't have shown these diagrams. They showed the carbon and temperature for millions and millions of years. Yeah, but what you see, the very general long-term trend is a slow decay in carbon. Yeah, we started with a very high carbon concentration, 5,000 or something like that, and then there has been a slow decay, but intermediate we had a very sharp decay in the what's that called, the Cambrium explosion, yeah, when life exploded, yeah, the Cambrium explosion, CO2 went sharply down, yeah, went really sharply down, but then after that it also rose again, sometimes pretty sharply, sometimes more slowly, and admittedly, I don't know. Are you familiar with Immanuel Velikovsky?
I am not. No.
You are not. It's before your time. He was highly disputed in the 50s. Yeah. Okay, I read his books later, but I am quite convinced of his theory. There have been quite a few very strong impacts, yeah, of collisions of meteorites and of very, very large impacts, yeah, which sometimes, I mean, you know that 60 million years ago, which created the Bay of Mexico, yeah, that was when the dinosaurs got extinct, yeah. There were other impacts before, which wiped out most of life on Earth, and also all the woods were burning. Yeah, the forests were burning, and so the coal was created. Yeah, and that means burning forests means that carbon dioxide was again released into the air. Yeah, and so there was quite a bit of ups and downs, but the very general, if you look very globally over the last, I don't know, few 100 million years, you will find a very slowly decline with a lot of ups and downs in between. Yeah, so we keep losing carbon in the air in the general trend, and the reason why it was constant over the last million years, the reason is that below 200, life is suffering terribly. And so 200 is kind of the lower limit. All the functions of life are slowing down, yeah, very much. And so this means it cannot really go much below 200. Yeah, that's what I think. Yeah, and so I fully agree with is it Patrick Moore? Yeah, and who says that burning fossil fuel is a blessing. Yeah, definitely, it's a definite, because we give life another chance. Yeah, that's definitely true. Yeah. But it will. I don't think it will go down much further than 200. But life will suffer terribly under these conditions. Yeah, and the 200 are always connected with very much cold times. Yeah.
So I think Ralph Ellis has said that if the CO2 concentration at sea level was 200 parts per million, if plants are trying to grow at 10,000 or 15,000 feet up on a mountain, there's less CO2. Is that correct? That they would have a harder time?
Yes, yeah. Oh, they would have much harder time. Yeah, yeah. Life would be much more restricted to sea level. Yeah. Yeah. Of course, yeah. I mean, the whole air gets thinner when we go up. Yeah, I mean, even if I don't know when you were last on Mount Everest,
Never.
Oxygen is quite thin there too.
All right. Last question I have. I'm still suspicious about this air bubble in ice. We think this bubble is 700,000 years old, and we think it has the same composition today as it did 700,000 years ago. Have we calibrated at all if we looked at air bubbles that are from 1960 or 1970 and made sure that they matched up with Mauna Loa? I think people say, oh, you can't calibrate it that way. It doesn't work that way.
I think people have done it. Not until 1970, but I don't know, until early 1950 or something like that. I think I cannot tell you for sure now. Yeah, but I think I have seen it. Yeah, I think I have seen it. I mean, it's a proxy. I mean, I don't know. Yeah, I mean, also the temperature proxy, we are not sure. Yeah, but currently it's the best we have. Yeah. We may be wrong. Yeah, but it gives at least my own work shows that it gives a consistent picture. Yeah, I mean, it doesn't contradict. It doesn't contradict the model which works for the current concentration. Yeah, it doesn't. So I'm confident. Yeah, without being dogmatic.
Do you happen to know that if that bubble is there, maybe under a mile of ice, what sort of pressure it's under? Because I don't know what would the pressure be down there.
I couldn't tell you. It depends if the ice. I mean, if the ice is thick. I mean, if there is, I think there should be increased pressure. Sorry, I haven't asked. I haven't asked this question yet.
Okay, I mean your presentation.
So
it wasn't about that.
I don't know the answer.
All right. Any other points you'd like to make about your actual presentation before we finish up here?
Yeah. Well, no, not really. I think it's a nice example. First of all, to make valid the effect of natural emissions, and I hope it will be a contribution also in the mainstream discussion. Yeah, that's what I'm hoping for. That there is someone sensible out there.
Oh, thank you very much. Yeah, I love your approach of just digging so deep into the data. I think it's fantastic. So thank you for what you're doing. Appreciate it.
Okay. Thank you for the invitation. And I always like to come back to you.
Sounds great. Let's do it again. So we'll talk to you later.
Okay.